Hey there, flyers. Welcome. This is brought to you by 69 Snowboard Detachment. Today we're going to talk really briefly about gyros and how gyros work, or at least the type of one that I got in my drone, and maybe the one you got in your drone. Here's a sensor. These magnetic lines of flux. And using the Coriolis effect, this sensor detects that, capacitively couples it through. Remember, with capacitance, it's going to do two things. It's going to block any DC on the line that's like maybe lurking from that antenna from detecting it. And it's going to pass the effects to AC. So you're going to take that little thing, that filtered signal. Now it's also filtered. It's basically, this acts like a resistor, that acts like a capacitor, that makes an RC filter. So basically what happens is you've kind of also made a little bit of a filter. You've got a low noise amplifier in here, and what it's going to do is it's going to amplify that signal without amplifying noise to keep the same signal to noise ratio. And basically what's going to happen then, you're going to go into a demodulator. And that demod is going to just look at the varying parts of that carrier, of that signal, and it's going to decode it into that RF carrier that's varying in frequency and phase. It's going to decode it into just a straight analog signal down here in the voltage range and not so much in the frequency range. What's going to happen from that point, you're just going to take and filter that, do some signal processing. That analog signal, make sure we don't got other noise picked up from the rest of the drone. And we're going to send it off to a 16-bit A to D converter. And with 16 bits, it can put out a pretty good digital word. Each sample can be a big digital word. So just real briefly, say you got a signal, and I'm sampling it here, and I'm sampling it here, and I'm sampling it here. And if I got 2 bits to represent this, say I got 3 bits to represent this, that's 2 to the third, or 2 times 2 times 2, it's 8. I got 8 possible levels that I can do. But if I've got more, I've got 2 because it's binary. But if I got 2 to the next level up, 2 to the fourth, 2 times 2 times 2 times 2, right, is 16. Now I've doubled my accuracy because I got 16 levels in there. And well, this good old A to D converter, it is not 2 to the fourth, it's 2 to the 16 because it's 16-bit converter. So it can have a very fine, number of levels. So it can be very accurate. So that when you reproduce the signal, you take just a bunch of pulses and you connect the dots. And there's a little bit of quantizing noise that you can't, depending on your sampler rate, you can't get exactly. And all that quantizing noise is less the more accurate your sample, the more accurate your levels are, and the more often your sampling is. So this thing is sampled. It's got a 16-bit A to D, and it's sampled at 8 kilohertz, 8,000 times a second. So you figure, even if it's the highest frequency that's going to be, detected from this, because there's not a lot of movement, that means it will have sampled it many, many times. So that when it tries to recreate it, it has many, many digital words. Each of these is a byte or a digital word, maybe an octet, or a double octet, because there's 2 bytes to represent each level. So this baby's just pumping out data. And that goes to the processor, and at which point the IMU or in the flight controller that can determine, okay, here's my gyro, here's my position. All based off of this little piezo-resistive coupling and the Coriolis effect. And yeah, that's my story, and I'm sticking to it. We'll see y'all for the next schematics. Bye now.